In the last section, we considered basics of iterative algebraic solvers incorporating matrix splitting. In this section, section 10.23, you will study relaxation methods. We'll begin with a formal definition of the matrix splitting. A matrix splitting is an expression which represents a given matrix as a sum of matrices, as in this equation, A is m minus n. Before dealing with relaxation methods, for the given matrix, we'll give names to parts of the matrix A. If we write down A is D minus E minus F, then here D is the diagonal. Minus E is lower portion, strictly lower portion, and minus F is strictly upper portion. So if we combine them, then that will be the same as the given matrix. So just is a sort of a names. The relaxation methods can be formulated by selecting m and n, so that A is m minus n, A is m minus n. For example, the Jacobi method select D for m, so that m must be E plus F. Now, Gauss-Seidel method select D minus E, which means the diagonal and the lower portion. Then the remaining part must be N, F. Now, SOR is choosing the lower part, and okay, 1 over W, the scaled diagonal. Usually for SOR, successive over relaxation, omega is chosen between 0 and 2, but omega is usually larger than 1. In fact, if it is smaller than 1, then it is called successive under relaxation. For successive over relaxation, omega is larger than 1, which means that whenever omega is less than 1, so 1 over omega D is a part of a diagonal and lower portion for m. And n is now, you can get, once m is chosen, then n is the same as m minus a. From this equation, you can find n. So these are coming from this equation. So we have 30 cases. We'll deal with these 3 methods step by step. Okay, here we have the Jacobi method. It is formulated with m is the diagonal portion. So n must be E plus F. Okay, we have this metric equation for the method, the old iterate. And by solving this metric equation, we can get new iterate. Now we consider ith component, the detail of the equation. Okay, let's see the metric D. D is, now first one is A11, it's a diagonal portion, and then A and N. Now the vector is now x1, go down at the end xn. Now there's kth one, and then now the right side. Okay, if we consider ith component, then this metric vector, this row vector dot product will be here. The only non-zero is aii, this diagonal entry, which is aii, so that aii xi. That is exactly this one. Now from this one we have a bi. Now from exk minus 1, now e is, okay, minus e is a lower portion. So the e has a shape, strictly lower part. E is this lower part and negation of that. And then now we have xk minus 1, this vector multiplication. Now consider ith component here. Then the product will be from here to there and from here to there. But this one is now j is I minus 1. From 1 to I minus 1. Now 1 to I minus 1 dot product along with this negation. That's exactly from e xk minus 1. The same way, quite similar way, f xk minus 1. F is now the minus upper portion and then vector over there. Then ith one is this and that product. So that is exactly now j is from I plus 1 to n. Here minus I a ij xj, j is from I plus 1 to n. That is coming from this one. Okay. Now we divide the equation by aii. Then we have xik and 1 over aii, and minus comes out, and we reach at this equation. This is now the component-wise equation for the implementation of the Jacobi method. Let's see the example. We have a matrix, and 2, 2, 2 along the diagonal, and minus 1 just below diagonal, and here upper portion also minus 1, and right side 1, 0, 5. And we start with x0, 1, 1, 1, initialization, and we try to run a few times in detail. The true solution for this algebraic system is 2, 3, 4. Here multiply 2, 3, 4 is 0, so that 4 minus 3 is 1, 2, 3, 4, 6 and minus 2 and minus 4, so that it will be 0, and 2, 3, 4, so minus 3 and plus 8 must be 5. So true solution is 2, 3, 4. We start from 1, 1, 1. Let's see the iteration details. Start with x0, 1, 1, 1, the initial vector, and we open x1, x2, x3, having length 3, and from x0, every x0, we try to get x1. Now, for the first component of the x1, the first component, we don't have lower portion, and we have only upper portion. So that is j is from 2, 2, 3. 2, 3, that is 2, 3. And then the bi from right side, we have the first one, and divide by a1, 1. That is exactly this formula. So we have only right now this portion when I is 1. Now I is 2, then b2 we have here, from here, and then now from this one we have one component. Now j is 1 to 1, so we have one component. From the upper portion we have also one component, which is now j is 3 to 3, so we have that, and divided by a2, 2. For the last component of x1 and last component, we have only lower portion. So j is from 1 to 2, and from right side b, we have a third component and divide by A33. So we finished one iteration and we got x1. If we print out, then that is 113. Now by using x1, now we can get x2. First component, second component, third component, exactly same way we do to get x2, and now the result is 1, 2, 3. Now by using x2, now again, exactly the same, and to get x3, and we have 3 over 2, 2, 7 over 2. We can implement the Jacobi method systematically here. Now in iteration, case 1 to the maximum iteration. Now once case 1, okay, in the beginning, now is initialized in the first copy. We try to make 2 copies of the solution. And once case 1, ID 1 is k plus 1 is now 2, modulo 2 will be 0, plus 1 is 1. Once case 1, modulo 2 will give 1, so that will be 2. Now ID 2 is 2. How about case 2? Then now 2 plus 1 is 3, modulo 2 will be 1, plus 1 will be 2. Now case 2, and this is 0 and 1. And now case 3, in iteration, there is again 1, 2. So it is a 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1. That means that we initialize, we save the initial value, initial solution in the first copy. We have 2 copies, 1 and 2 of the solution. We initialize it here. There's a copy 1, there's copy 2. And by using this one in the first iteration, we try to get here now, there is x0 in the beginning. Now we have x1. Now by using x1, we try to copy again back so that we have now here x2, and then, and okay, that rather than subscript, superscript, okay. Now by using x2, again, by using this one, we get x3, and x3 is saved here. So in this way, back and forth, we try to update the value. That's one strategy to implement the Jacobi method. Okay. Now, along with this implementation, let's see the result after 10 iterations. And 3-dimensional metric and right side, the initialization, and 10 iteration. So after 10 iteration, we reach here now 1.9375, and happen to be the same anyway. So we can measure the error from the exact solution, which is 234, and now the maximum difference is 0.0625. We'll use this algebraic system again for Gauss Seidel and SOR. Let's see how they perform differently. Now, the Gauss Seidel method. The method is formulated with M to be the diagonal portion and lower portion, and corresponding N must be negative upper portion. So we have here the vector equation. We'll move this one to the right side. So we reach at that equation. Now we consider the detail, the ith component, the line by line. The ith component, then exactly same as for the Jacobi method, that will be AII XI. Now from this one, bi. Now from this one, now lower portion, negative lower portion, but new value rather than xk minus 1, we are using xk values, the updated values for this portion. So only the difference from the Jacobi method is rather than k minus 1, we are using here k. Now for upper portion, the same as for the Jacobi method. Now the question is it okay? Now we are using here the updated value. Now assume we are computing the solution from top to bottom. Now algebraic system, so that we start with is1, is2, is3, is4, and so on. Then once we reach at some I, then earlier values, because through here, now the row from 1 to I minus 1, now x values are updated. Already we got the values. So here j is 1 to I minus 1, xj are updated. So updated value will be used. They are available already because we are going down one at a time. So that at the ith position, these are all available. Is it clear? Yeah, it's clear. Now, AII is now eliminated from that one by divided by AII. Then we reach at that one. Okay. The difference is that the Gauss-Seidel method utilizes updated values, which makes not only its convergence faster, but also its implementation simpler. So let's see how it is working. Now, for Gauss-Seidel, now we are using updated values so that we don't have to make another copy of the solution. And just as simply, after computing the quantity xik by using the formula, we just save at the same position and as the earlier xk minus 1, then it is updated. And then in next line, it will be used. So that is updated value will be automatically used. This implementation is simpler. And because the updated values are used, in reality, convergence will be faster. Let's see the performance of the method. Okay. Now, for this Gauss-Seidel method, the same metric, same initialization, same 10 iterations. Then, here, we reach at the error is now 0.0039, so it's way smaller. In fact, if we are, when we are using Jacobi method, 10 iteration made this level of solution. So that 10 iterations of the Jacobi method is the same as or similar to 6 iterations of Gauss-Seidel method. 6 is not really half of 10, but mathematically, Gauss-Seidel method is twice faster once you try to solve and up to the convergence. So asymptotically, twice faster. It's well known from the numerical linear algebra. By comparison with the result of the Jacobi method, we can see Gauss-Seidel method is faster. It's theoretically known that the Gauss-Seidel method is asymptotically twice faster than the Jacobi method. Okay, now we'll go to the final example, successive over relaxation, SOR. Now for SOR, choice for M is 1 over omega and D minus E, lower portion of the metric, and then part of diagonal, because omega will be larger than 1. So the part of diagonal, and n is obtained in this way. Now we write down the metric equation, the metric vector equation. Then this is iterative algorithm. 1 over omega is used, so that rather than 1 over omega, we multiplied omega everywhere. So we recheck this equation. Now we rearrange these terms. Then we recheck this one. Now dxk and 1 minus omega dxk minus 1 and omega, and that portion. Now this one, once we multiply the inverse, then disappear, and there's a d inverse, which is divided by aii for ith component. So that now, but anyway, for each component, ith component, we have that. And now after divided by aii, we can see that this one is actually the same formula for the Gauss-Seidel method. So in a sense, after divide by aii, now here aii, and this is Gauss-Seidel update, and then after getting Gauss-Seidel update, we try to extrapolate along with xi k minus 1, Gauss-Seidel update, and omega, and 1 minus omega. Omega is between 0 and 1, that is interpolation. However, omega is larger than 1, then that is extrapolation, so that the weight is larger here, so that once it is, okay, so if we consider this quantity and that quantity, then, okay, it's made in this way. xk minus 1 is here, and now Gauss-Seidel update is here, then extrapolation will be outside over there, right? So that, okay, this is xk minus 1, that is Gauss-Seidel update, then there's SOR update is given outside in this way. So it is extrapolation. So the implementation is not so much complicated. From Gauss-Seidel, you can easily get SOR. And once you have Gauss-Seidel algorithm, then you have this line in your implementation. Now you save it into a temporary value, and then extrapolate with the older value and update. Of course, this update will be saved in the same spot. Once omega is 1, then the SOR becomes the Gauss-Seidel method quite clearly, right? The SOR is an extrapolation scheme based on the Gauss-Seidel method. So the reason this extrapolation is working better is here. And in most cases, the algorithm is monotonic. Okay, I'll explain the algorithm properties. If you are using such a relaxation method, then, for example, it's a domain, and you are the desired solutions like that, then assume you start with initialization 0. Then each iteration is coming up, again coming up, again coming up, like that. So it's gradually becoming larger, larger, larger. So reaching at that one. So that is, so that I can say the solution is like monotonically improved there. So that rather than from here to, for example, new one is updated by using Gauss-Seidel, then rather than decide this one, and from old one and new Gauss-Seidel, then extrapolation, so it can go further. Now, you may try to choose omega large so that you can go jump very fast. However, once you reach at, for example, around there, and old one is here, now new solution is here, then if you have omega larger than 2, then the distance will be over there. And then now, and it's 2, then it's the same distance you are updating like that. But larger than 2, then far away. And then from here, if you try to update it, then you may go down. Then again, extrapolation will be much go down, so that your solution will be oscillatory, which means that it's not stable and not convergent. And from the beginning, in most cases, blowing up. So you have to choose the omega not larger than 2. Even it cannot be 2. And so that once you reach it from here and reach it over there, smaller than 2 means that even though you extrapolate an upper portion over there, the distance is smaller than this distance. So that even though around here, oscillation is becoming smaller, 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 and then reach at the desired solution. Anyway, extrapolation is working because of the monotone property of solution update. Okay, that is geometric or some interpretation, but theoretically also we can prove that omega cannot be larger than or less, same as 2. It must be always between 0 and 2, excluding the boundary. Okay, here we have an implementation of the SOR. Now, okay, that is exactly Gauss-Seidel implementation. And we make here in temporal array, or you can make this whole thing at this position. Anyway, now temporary value and extrapolation and save at the same spot, so that in later, so when I is now going much forward, then this value will be used to update the way. Okay, that is an implementation for the SOR method. Let's see how it is working. Okay, for SOR, we choose the same metric, same right-hand side, the same initialization, and 10 iteration. For omega, we chose 1.2. Look at here. After 10 iteration, wow. Now error, maximum error becomes 4.5 times 10 to the minus 7. And Gauss-Seidel is a 3.9, 10 to the minus 3, and Jacobi and 0.0625. So SOR is way better than Gauss-Seidel or Jacobi. Of course, Gauss-Seidel is twice faster than Jacobi, but SOR is way faster than Gauss-Seidel. In this example, we used omega 1.2. Now, anyway, along with that is way faster than Jacobi and Gauss-Seidel. The question is, how can we find the optimal parameter omega hat? We'll see it soon. Now, we have here convergence theory for any initialization x0, the sequence defined by this equation converges to the unique solution if and only if the spectral radius of this iteration metric is strictly less than 1. In this case, the iterates satisfy this inequality. This norm doesn't have to be less than 1. However, in any case, we can write in this way. And now, if and only if the convergence is the same as the strictly less than 1 spectral radius. Now, for this T, for Jacobi method, we have that. This is a metric equation. However, we don't use this one here. We already know the component wisely. We can find the updated equation and we implement it. We never use such a metric, but for theory purpose, we write down this form. And for Gauss-Seidel, the iteration metric is given here, and for SOR, this is the iteration metric. Here we have the Stein-Rosenberg theorem. These 4 equations or inequality is satisfied exclusively. Only one case is true. That means once spectral radius of Jacobi iteration metric is 0, then for Gauss-Seidel, its spectral radius must be also 0. So it is a relationship between Jacobi and Gauss-Seidel. For one method, the spectral radius is 0, which means all eigenvalues are 0. Then for Gauss-Seidel, again, all eigenvalues must be 0. Now, spectral radius of Gauss-Seidel is between 0 and 1. Then now the other one also between 0 and 1, and then Gauss-Seidel spectral radius is smaller than the Jacobi the spectral radius. Once one of them is 1, then the other one must be 1. That means now from this one is not converging. However, anyway, one of them has spectral radius 1, then the other one should. And now this line 4 means that one of them has spectral radius larger than 1, then the other one should have larger than 1 in the spectral radius, and then now Gauss-Seidel spectral radius must be larger than Jacobi's. Once it is convergent, then Gauss-Seidel converges faster. Once they diverge, then Gauss-Seidel diverges faster. For symmetric matrices, SOR spectral radius is strictly less than 1, which means that SOR is convergent. Then A must be party definite, symmetric, and the party definite means that all eigenvalues must be positive, and now the omega must be between 0 and 2. So when you are using SOR along with omega between 0 and 2, and always is convergent for symmetric metric, then the metric must be party definite. And also, once you know the metric is party definite, then if we choose omega between 0 and 2, then the SOR will always converge. Okay? The meaning of the theorem is quite clear. Now we have optimal omega for the SOR, successive over relaxation. For algebraic systems of good properties, it is theoretically known that the convergence of the SOR can be optimized when omega hat is chosen by this one. SOR is the iteration metric is not simple. However, for Jacobi, because it's using only diagonal, and so the inverse of diagonal is quite easy, so that you can roughly estimate the spectral radius of the Jacobi iteration metric. Then, if you know this value, then by using this formula, you can decide omega hat. So theoretically, it's known. However, in real life, we can find practically better omega for given algebraic system. In modern implementation, omega hat is dynamically changing. In the beginning, user can give an initialization of the omega value, and then during the iteration, after several iterations, it's trying to adjust omega value, and then eventually the omega hat is obtained. But that is practically best working omega value. So along with that choice, SOR is extremely fast. Okay. When omega is larger than 1, the blending of the SOR, the second equation of 1036, let's see here. Okay, that one, so that, and that is a sort of a extrapolation. Okay, that is an extrapolation. It is how the algorithm is named. On the other hand, if omega is less than 1, then it is a kind of interpolation, also under relaxation. Extrapolation is trying to jump a little bit farther. However, once you are trying to interpolation, then a sort of is pulling down, so it's dragging in a sense, so that it is under relaxation. So algorithm is also called the successive under relaxation SOR. Okay, that's the end of the section. Thank you.